So my name is Dr. KCH Apparao, working as a associate professor in mechanical engineering department. In previous class was discussed the introduction of boiling and condensation process. In this class, we'll see the boiling process. What is the importance of the boiling process, and what are the types, and what are the stages in boiling process? We'll see, and we'll solve some numericals based upon the boiling process also. So in last class, already I told that. So in convection, so previous chapter we know that in convection we'll see only heat transfer only. It means heat transfer from one surface to another surface, or solid to liquid. So these are the convection process. But in boiling and condensation, we already discussed in previous class also. We will see the phase change including the heat transfer. Phase change, it means uh, water is converted into vapor, or vapor is converted into water. Suppose along with the heat transfer, the water is converted into vapor, so that is called boiling. So in boiling, we'll see heat transfer along with the phase change. So latent heat is associated with the phase change here. You know this one. So okay, boiling. So here we'll see the heat transfer, rate of heat transfer. We'll see that is the Q, or heat flux along with the phase change. It means water is converted to vapor. So in last class we discussed the phases of the boiling curve. These are the boiling curve. So boiling occurs in three phases. The first one is the interface evaporation. So simply called as the free convection. Free convection. You know the convection. What is convection? What are the types of the convections? Convection process. We already discussed in previous classes also. So second one is the nucleate boiling. What is the importance of the nucleate boiling? What are the phase change different to phases in nucleate boiling? So third stage is the film boiling. Film boiling. Once again, I want to repeat this one. First one is the interface evaporation or free convection process. So here we'll see just like this is the container, water is placed here. So flame is like this one. So in evaporation or free convection process, you know that convection process, in free convection process, when the particles are heated, the density of those particles will be decreased, because density rho is in direct proportional to temperature. You know this one. So if the temperature increases, density will be decreases. Less density particles moves into upward direction. Heavy density particle moves into downward direction. So this less density particle, which are heated particles, moves into upward direction, and the heavy density particles moves into in this direction. In this way, this water is evaporated here, just like flows evaporated here. Here for the boiling, the condition of temperature is the temperature of the solid surface must be greater than the saturation temperature of the water. So when the temperature of solid surface is greater than the saturation temperature of water, we will see the boiling process. So otherwise only will see only natural convection process only. So suppose here we will see this temperature difference, we will see delta T is the TS. It means solid surface temperature minus liquid surface saturation temperature. Okay. If the TS is greater than the saturation, T saturation, then we'll see the boiling process. Okay. Here just like temperature difference, excess temperature, we call delta T is the excess temperature. This excess temperature is very low, that is 0 to 5 degrees Celsius. Okay. So in this range, you will see the interface evaporation or free convection. Here we will see just like evaporation of into uh, water into vapor. Okay. So this is the uh, first phase. So next phase, second one is the nucleate boiling. We'll see in the first phase here also from starting to here gradually heat transfer rate of heat transfer here are heat flux. You know that the heat flux is the small q is equal to heat transfer by uh, area. So q by a. So this q by a heat flux is gradually increases. Okay. So next one is the nucleate boiling. In the nucleate boiling, we'll see two phases. First, phase one, that is the here we'll see the bubble formation. You can find out the bubble formation when the excess temperature delta T E is greater than the delta T is greater than, it means so the range of the delta T is from 5 to 10 nearly. So 10 degrees Celsius, you will see bubble formation will be occurred here. So this is the stage 2. Here we will see the bubbles formation. The bubble formation, it means so the water which are very near to surface, the water will be heated automatically. Those particles or the water is converted into bubbles. These bubbles, because the density of the bubbles is very less, the bubbles moves into upward direction. When they are moving at some time, these bubbles will be condensed or will be converted into water, because uh, the water which is near to surface, so those water temperature is very high, but the water which is far from the surface, the temperature of those water, that water is very less. It means less than the saturation temperature. So automatically these bubbles will be condensed. These bubbles will be formed as a water. So it means this bubble doesn't reach the top surface of water. So that phase we'll see in second. Here bubbles, it means bubbles formed, but bubbles will be condensed due to less temperature of the water. So that is the phase 2 in nucleate boiling. So but here also heat transfer rate or heat flux will be gradually increases. Third phase, phase 2, that is the bubbles rise to surface. It means when the temperature, excess temperature is increased greater than the 10 degrees Celsius, automatically bubbles formation will be increased. These bubbles will rise to top surface. Automatically water is converted into vapor. So that phase we'll see here also. So gradual rapid bubbles will be formed, and these bubbles will reach to top surface. Automatically those bubbles moves into air. So from the high density to less density air. So you'll see that is the phase 3, that is the bubbles rise to surface. So up to this one, we'll see gradual increasement of or increase of heat flux or q, small q. So here we'll see the heat flux will get the top point or high point. So this point is nothing but a critical radius of temperature. Okay, so this is the critical radius of temperature, critical point. Let's see. So after this nucleate boiling, we'll see the film boiling. In the film boiling, it means the in fourth stage, it means here unstable film. We'll see unstable film means so in the phase after the nucleate boiling, the high rapid bubbles will form. These bubbles will rise to the top surface of the water. Those bubbles, it means so in this way, just water is converted into vapor. But the more bubbles are formed, those bubbles are combined with each other and form a just like films on the surface of this container. Okay, like this one. So these films, these are the unstable films will form. So these films just opposes the coming of water particles into the towards the surface. Automatically, it means so these film conductivity, the conductivity of this film is very less compared to the water. So water conductivity is very high. Film conductivity, so gas conductivity is very less, you know this one. Due to this कारण, due to this reason, automatically the heat transfer rate will be decreases. It means so the heat transfer from the solid to liquid opposed by these films, because the conductivity of those films, those gas films, will reduce the heat transfer rate from the solid to liquid particles. So automatically, gradually, heat transfer rate will be decreases. So in next stage, so here we'll see the stable film. So stable film means these small films are combined and act as a just a blanket of the on the surfaces. It forms a big film. It covers the surfaces, covers the surface. Okay, so automatically the heat transfer rate will be decreases. So it reaches one minimum point. This is the minimum point. So after that, we will observe that one, the heat transfer rate will be increases gradually or rapidly, because this film, this blanket of film act as a just like some solid surface, and the radiation takes place between these two surfaces. It means solid surface and the film. So heat transfer occurs due to the radiation process instead of convection process. So heat transfer takes place from the solid surface to film, film to these particles, liquid particles. So automatically heat transfer rate will be increased graphically. So this is the just like process of boiling. We already saw this one. So this is called excess temperature. You know this one. This is the graph of excess temperature and the rate of heat transfer or heat flux. Okay, we will see some few points in these three phases. This is the same process. We can see here only we'll see the vaporization only due to the natural convection process, natural convection boiling process. So here we'll see bubble formation. So here we'll see rapid bubble formation. So it is the critical heat flux here. So critical heat flux. So next, due to these vapor pockets or vapor pockets, these vapor pockets opposes the heat transfer rate from the liquid to solid or solid to liquid. So heat transfer rate will be gradually decreases. This is the point. So this is the minimum point of heat transfer rate. So then we will see the complete covering of vapor film on the surface. This vapor film acts as a some just like small solid surface. Then radiation occurs between the solid surface to vapor film. So due to the radiation process, heat transfer rate will be increases gradually. This is the process. You know this one. We here will see the range of temperature up to 0.5 5 degrees Celsius. Here up to 30, at 30 degrees Celsius you get the maximum critical heat flux. So next to the excess temperature is increases. So next to gradual decrease and rapid increase of heat transfer will observe here. Okay, these are the points already explained this one. The first phase is the interface evaporation, next to boiling and film boiling. So interface evaporation, you know that here there is no bubbles. Here only excess temperature is only 0 to 5 degrees Celsius. Okay, it's very near to saturation temperature. So in this region liquid near the surface is superheated lightly, and convection currents circulate the liquid and evaporation takes place at the liquid surface. Already explained this one. The surface temperature must be somewhat above the saturation temperature. Without surface temperature, it means Ts is greater than T saturation, then we will see the boiling process. So here, so next one is the pool boiling, nucleate boiling. We already this is the range. So point A to C, we already saw this one. That is the 5 to 10, next to 10 to 30 degrees Celsius. This is excess temperature. 5 to 10 will see the bubbles formation, but those bubbles collapse and formed as a liquid because of less temperature of the liquid. It means the temperature of liquid or temperature of water is less than the saturation temperature. Then we will see the after 10 degrees Celsius we will see rapid bubble formation. Then we will see the um, rapid growth of heat transfer. This is the maximum point of heat transfer or heat flux. So this is called critical heat flux. You know this one. Then due to the film formations, the heat transfer rate will be decreases. Okay, this is the process already discussed. Okay, nucleate boiling. So next one is the film boiling. So initial natural convection process, boiling. Next one is the film boiling, next nucleate boiling and film boiling. These are the stages in this boiling process. Okay. Now we'll see finding the rate of heat transfer in boiling process. Here in the nuclear fuel boiling, uh, heat flux, how to find the heat flux. So rate of heat transfer per unit area, heat flux. So because here this is the formula, because we know this one, boiling is depend upon the properties of the liquid and surface properties and the surface roughness condition also. And because these parameters, surface properties and the surface roughness properties include so many parameters, and liquid properties are very high. So we have to include all these things for the finding of all these properties for finding of the uh, heat flux. So this is the formula for the heat flux. So this one is the first one is the mu L, liquid viscosity. Uh, so you know that heat flux, viscosity, liquid viscosity. Next, you know this one HFC is the uh, enthalpy of evaporation. You know this one. G is the acceleration due to gravity. Rho L is the liquid density, saturated liquid density. Rho is the just like saturated vapor density by sigma. Surface tension. This is the parameter to form the bubbles in circular form. So we have to consider this one also. Then so whole to the power of 0.5. It means under root. Next to CPL is the specific heat of saturated liquid. Delta T is the excess temperature. You know this one. Temperature difference between solid surface to saturation temperature of the liquid. Ts minus T saturation. This is the value of delta T excess temperature. Next to CSL is a surface fluid constant, and HFG, you know this one, this is the enthalpy rate, and PR, Prandtl numbers, you know this one. So we have to consider all the parameters, and by using those parameters we can find out the heat flux. Okay, so surface heat flux, this one is the, by you can use this formula to solve the different numericals. So next, how to find the critical heat flux. So you know this one, critical boiling point, so where the heat flux is very high. So critical heat flux for nuclear fuel boiling. Okay. So this is the formula. Heat flux PSC, critical heat flux is equal to 0.18 into rho V, density of evaporation, HFG, enthalpy value, and G is the acceleration due to gravity. So sigma is the surface tension, rho L is the liquid density minus vapor density. So all to the power 1 by 4. By using this formula, you can find out the critical heat flux. So next one is the film boiling uh, rate of heat transfer. Hmm. So finding of H value, heat transfer rate, coefficient of heat transfer. Sorry. So how to find out the coefficient of heat transfer? Okay. So H convection is equal to 0.62 into, so vapor thermal conductivity. So because that acts as a solid surface, the due to radiation, uh, so heat transfer will occur. Okay, so this is the case, the thermal conductivity of the vapor. Rho B is the density of vapor. Rho L is the density of liquid. So G is the acceleration due to gravity, enthalpy, and so these are the values. By using these values, you can find out the film boiling. So by using these formulas, we will solve few numericals here. We'll see first one. We'll see first numerical. So a wire of 1.2 mm diameter and 200 mm length is submerged horizontally. So in water at the 7 bar pressure. The wire carries a current of 135 amps with an applied voltage. The voltage is equal to 2.18 volts. If the surface of the wire is maintained at 200 degrees Celsius, so surface temperature Ts is equal to 200 degrees Celsius. So I have to find out the heat flux. So heat flux is equal to rate of heat transfer by area. So Q by A. So Q by A, Q, you know this one, Q is equal to, according to convection process, HA into temperature difference, delta T. So HA into delta T is the saturation, solid surface temperature minus T saturation temperature. Okay. So first of all, you have to note the all the parameters or the data given in the numerical. Wire diameter small d 1.2 mm convert into meters. Okay, 0.0012 meter. Okay, so length also should be converted into meters. So L is equal to 200 meters. So 0.2 meter submerged horizontally in water at 7 bar. So current value also amperes has given. I is equal to value is equal to 135 amps, and voltage V is equal to 2.18 volts. You know this one, V into I, voltage into current, that is nothing but heat, rate of heat transfer. That Q is equal to V into I. By using this formula, you can find out the Q. Okay. So you can find out the area. Area is equal to pi dl. You know this one. So pi dl. Diameter has been given and length also has been given. Okay, pi, the value of pi. So by using this data, you can find out the uh, rate of heat transfer. What is the first one is the heat flux. It means Q, small q, capital Q by area. Next to boiling heat transfer coefficient, H heat transfer coefficient, you have to find out. H is equal to small q by temperature delta T E, temperature difference, excess temperature difference. So we'll see how to solve this one. So this is the given data. So diameter is equal to 1.2 mm has been given. So convert into meters, that is the 0.0012 meter. Length is equal to 100 mm. So convert into meters, that is the 0.2 meters. Next to current I is equal to 135 amperes, and voltage also given, that is the 2.182 volts. Next to TS, surface temperature is equal to 200 degrees Celsius. Then Q. So this one, Q is equal to voltage into current. So the voltage, that is the voltage is equal to 2.18 into current is equal to 135. So the value of Q, heat transfer rate. So that is the 294.3 watts. So next to area. So this is the pi dl. Area is equal to pi dl. Pi into d. D value is equal to 0.0012 into length is equal to 0.2. Okay. So then area is equal to 7.54 into 10 to the power of minus 4 meters square. So this is the area. If you know the Q and A, so then heat flux, heat flux Q is equal to Q by A. Okay. So Q, the value of Q, 294, 294.3, 294.3 divided by area is equal to 7.54 into 10 to the power of minus 4. Okay. So this is the heat flux, 0.39 megawatts per meter square. So next we will see the, what is this one? H value, coefficient of heat transfer coefficient. H is equal to small q by delta T. Delta T is the surface temperature minus saturation temperature of the liquid. So the values, these two values has been given. This one. So first Q value is the value of Q is equal to 0.39 into 10 to the power of 6. Sorry. So watt per meter square. So saturation temperature, not saturation temperature. This is the solid surface temperature. Solid surface temperature is equal to 200 degrees has been given. So next one is the saturation temperature. This saturation temperature. So saturation temperature. Uh, so water saturation temperature, you have to consider this one. So based upon the at 7 bar pressure. So from the data book, you can collect this one. That is the 164.97 value. So by using this values, you can find out the H. H is equal to 1133.3 watt per meter square, Kelvin or degree Celsius. This one. So heat transfer rate. This is the value. So this is, it means initial condition of boiling. Here we'll see the convection process and phase change also. Okay. Now we'll see nucleate boiling and pool boiling numericals also. So one more numerical we'll see. An electrical wire of 1.25 mm diameter and 250 mm long is laid horizontally, submerged in water Here also fluid is equal to water. At atmospheric pressure, so 1 atm. The wire has an applied voltage of, so voltage also given 18 volts, and current I is equal to also given. Same type of numerical amps. Find the heat flux. Excess temperature, here you have to find out the excess temperature. Okay. So you know this one, heat flux Q is equal to capital Q by area. Capital Q is equal to heat transfer rate, voltage into current. So you know the voltage 80, current is equal to 45. Okay. So we can find out. Then we have to find out the excess temperature. For excess temperature, this is the formula. So for the boiling heat transfer coefficient, H is equal to 1.58 into Q by A, heat flux whole to the power of 0.75. Okay. You know this one. So Q is equal to area into delta T. Then delta T is equal to Q by A. So in place of Q by A, you can write the delta T. So H is equal to 1.58 into delta T E whole TUQ. Okay. So, so this is the formula. By using this formula, you can find out the delta T. So heat transfer coefficient also you can take from the data book. Okay. So this is the given data. This is the finding of Q. So capital Q is equal to V into I, 810 watts. Sorry. So surface area of the wire AS is equal to 5 dl. So 5 dl is equal to, the value is equal to 9.817 10 to the power minus 4 meters square area. Then small q by A, heat flux is equal to 0.825 megawatts per meter square. So next, finding of excess temperature is very important. So this is the formula, you know this one. Okay. So you can write to like this one. So 1.58 Q by A whole to the power of 0.75 is equal to, the value is equal to like this one, 5.62 delta TE in whole Q. So by using this formula, you know the Q value, A value, and you have to find out the delta T. So delta T is equal to, this is the value, so 19.68 degrees Celsius. So in this way, just like we can find out the rate of heat transfer by using data, and excess temperature delta T, and the heat flux also we can find out. Okay. So next we will see another numerical. So a nickel wire of 1 mm diameter, nickel wire diameter has been given, 400 mm long, length of the wire also given. So carrying a current is submerged in water. Here also fluid is equal to water, which is open to atmospheric pressure. Pressure of the water is equal to atmospheric pressure. So calculate the voltage at burnout point if at this point the wire carries a current of 190 amps. Okay. So you have to find out the critical heat flux. Critical heat flux. You know the formula for the critical heat flux, QSC, surface critical heat flux, is equal to 0.18 into rho V, density of the vapor, whole to the power 1 by 2, enthalpy into G, acceleration due to gravity, sigma surface tension, rho L minus rho V, whole to the power 1 by 4. So all these parameters, density of evaporation, enthalpy, and the G and the sigma. So we have to take from this data from the data book based upon the given temperature and pressure. So we'll see the physical properties. These are the given data. You can find out the Q value here because Q is equal to V into I already given. Okay, but at point of critical heat flux, you have to find out the voltage also. Next one, you know that the thermal physical properties of water at saturation temperature of water, that is 100 degrees Celsius, based upon the atmospheric pressure on atmosphere. So rho L and rho F. So density of the liquid and density of vapor is equal to 958.4 kg per meter cube. Density of vapor is equal to liquid and fuel both are same in water. Density of vapor is equal to 0.25955 kg per meter cube. Enthalpy is equal to 2257 kilojoule per kg Kelvin. Surface tension is equal to 58.9 into 10 to the power minus 3. So by using this data, you can find out the critical heat flux. Okay. Voltage at the burnout point, you have to find out voltage. So first of all, you have to find out the critical heat flux. So critical heat flux, by using that data, you can find out the critical heat flux. Okay. Then voltage, voltage at a critical point, critical heat flux. So Q is equal to voltage VV. You have to find out this one. Okay. Small q is equal to Q by A. So Q is equal to VB into I by A. Okay. So this is equal to QSC, heat flux at a critical point, critical temperature point. So by using this formula, you can find out the VB. VB is equal to area into QS by I. So current. Area is equal to pi d l. QS is equal to already we find here. If you substitute these values, you will get the voltage at a critical point, at a critical heat flux. So this is the way. So okay, these are the different references books related to this heat transfer. You can refer these books. Thank you for watching this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.